Our presenter today is John Lewis, Global Content Marketing Manager for Vision Products here at Cognex. He's been with Cognex for 11 years and was formerly a technical editor for an engineering magazine. He's been writing about machine vision, factory automation, and other technology topics since 1996. He's published hundreds of articles in dozens of trade journals and holds a BS degree in chemical engineering from the University of Massachusetts Lowell. Welcome, John.
Thank you for the nice introduction, Karen. Good day, everyone. I'm John Lewis, and I'm very pleased to welcome you to our webinar, Introduction to Machine Vision. I hope that you'll all find today's presentation to be informative and helpful in learning a little bit more about machine vision. We have a lot to cover on today's agenda. I'm going to talk about what machine vision is, the types of machine vision, and the kind of problems that can be solved with it. We're also going to cover the why of machine vision. What benefits can it bring to the factory floor, and why manufacturers use it? Finally, we'll talk about major components of vision systems and go over some basic vision definitions and hopefully some concepts that will be able to help you improve your vision system performance. So let's get started with the definition of machine vision. The Society of Manufacturing Engineers defines machine vision as the use of devices for optical non-contact sensing to automatically receive and interpret an image of a real scene in order to obtain information and or control machines or processes. So what exactly does that mean? Well, when I think of machine vision, I'd like to think of it as the automatic extraction of information from digital images for process control or inspection of manufactured products. Widespread use of machine vision started in the early 1980s when Cognex developed and sold its first commercial vision system. That system was for reading alphanumeric characters and codes on semiconductor wafers. Of course, machine vision has come a long way since then and is now used in many different industries for manufacturing everything from computer chips to potato chips. To better understand machine vision, imagine a manufacturing production line with a steady flow of objects, such as a bracket on the left or the oil filters on the right. A machine vision system would include a camera trained on the line and proper lighting so that the camera can see the necessary details. During operation, the machine vision system captures digital images and analyzes them against a defined set of criteria. It's important to decide what kind of result you want from your machine vision system. Results can be either analog or digital. The bracket example is analog because the output is the width of the center tab in millimeters. Other examples of analog outputs would be things like coordinates indicating a location or an ID number of a part. The oil filter application here provides digital results, essentially a pass-fail, good-bad, or a part A, part B type of output. Because essentially, if any of the holes in the oil filter are blocked, the part fails the inspection. Manufacturers use automated machine vision primarily for the purpose of image analysis. That is to analyze images and then either make decisions, such as is a part good or bad, provide answers to questions like, what is the gap measurement on a spark plug, or provide location information to guide a robot or align parts in a process. So where is machine vision used? Machine vision technology really cut its teeth in the automotive, semiconductor, and electronics industries during the 1980s and 1990s. But today, reduced complexity and cost is driving rapid expansion into new areas, such as heavily regulated healthcare and consumer product industries, as well as new areas such as shipping and transportation, where it is used primarily for barcode reading and package sorting. Why use machine vision? Well, it's a given that virtually every product that is manufactured in high volume or at high accuracy or that has to be made at very low cost can be made better, faster, and less expensive using machine vision. But besides improving quality and reducing cost, there are many other reasons to use it. On high-speed production lines, of course, speed is the primary driver. Machine vision provides consistent results while inspecting hundreds or even thousands of parts per minute. In clean room environments, preventing process contamination by humans is the driving factor. In hazardous environments, human safety is the reason to use it. Machine vision is also very well suited for microscopic inspection because with the right camera resolution and optics, a machine vision system can easily inspect objects that would be way too small for manual inspection. Machine vision is also great for closed-loop process control and robotic guidance. One other key advantage of machine vision, especially in gauging applications, is the fact that there is no physical contact between the parts being measured. This prevents damage to parts and eliminates maintenance associated with wear and tear on mechanical gauge surfaces. There are many benefits to machine vision that really can help achieve many different strategic goals. Higher quality product allows manufacturers to command price premiums, gain market share, and retain existing customers. Increased productivity and efficiency, production flexibility for mixed model processing. Machine vision helps reduce downtime. For example, a packaging line may automate product changeovers for different size packages by programming them in advance. Process control for tracking working process or uniquely identifying products so that they can be tracked and traced throughout the manufacturing and stocking process. Machine vision can be very helpful there. Lower capital equipment costs and production costs are another benefit. Reduce scrap costs and higher process yields that result from catching and correcting assembly errors. Minimize waste by rejecting flawed parts before adding value. If you catch defects early in the production process, you'll reduce waste because bad parts can be identified and eliminated before they are built into larger assemblies. You'll avoid scrapping expensive materials and reworking parts. Inventory control. Typically, if you can identify all of the pieces in a process, you'll require less stock and product becomes available more readily for just-in-time delivery. Machine vision uses decode tools to read 1D and 2D symbologies, as well as OCR to track parts and products. This helps manufacturers to avoid component shortages, reduce inventory, and shorten delivery time. And reduce floor space is another benefit. Let's see. Machine vision application categories. Now, an easy way to remember machine vision application categories is to think of the acronym GIGI. GIGI stands for guidance, inspection, gauging, and identification. Guidance is when machine vision is used to report the location and orientation of a part. Machine vision systems locate parts in 2 or 3 dimensional space and provide the robot controller with position information to adjust the robot path. This achieves far greater speed and accuracy in applications such as placing parts on or removing parts from pallets, picking parts from a conveyor and placing them in a package, locating parts and aligning them for assembly with other components, or placing them into a work cell, or even picking parts out of bins and aligning and feeding them into a process. Another type of guidance application would actually be used for large part inspection, such as using a robot to either manipulate the part or the camera to inspect critical features of the large part or assembly. The key advantages of vision-guided robotics are elimination of costly fixtures to reduce capital investment and improve productivity and manufacturing flexibility for mixed model processing, which essentially allows manufacturers to make multiple products on the same production line. Another very powerful feature of machine vision is called tool fixturing. This is where the vision system is able to locate at least one feature on a part for the purpose of calculating the XY position and rotation of the part, and then use that location information to position the other vision tools precisely on the part within the image. Before we continue on and talk about inspection, gauging, and identification, the other 3 machine vision application categories, I wanted to step off a little bit on a tangent here that's related to guidance, and that is geometric pattern matching. Because location information is used for aligning other machine vision tools that we use during the process, it's really very important for pattern matching tools to be able to tolerate large variations in contrast and ignore lighting changes or scale changes, rotation, and other variations while being able to reliably find the part every time. Part location software tools find the part within the camera's field of view, and this is typically the first step in any vision application, whether it's the simplest assembly verification application or a complex 3D robotic bin picking operation. Locating the part is often the most critical step. Part location really determines the success or failure of the application, because if the machine vision system can't locate the part within the image, then it won't be able to guide, inspect, measure, count or identify the part. While finding a part sounds simple enough, locating parts in actual production environment can be extremely challenging due to appearance changes. Vision systems are trained to recognize parts based on a pattern, but even the most tightly controlled manufacturing processes allow some variability in the way the part appears to the vision system. Therefore, the vision system's part location tools must be intelligent enough to quickly and accurately compare training patterns to the actual objects moving down a production line and tolerate these variations. Because the vision tool alignment or fixturing aspect of machine vision systems, because of this, your parts can be facing all different directions as they go down your production line. And as long as you have a very robust pattern-matching tool, you can still locate it, fixture the subsequent vision tools properly within the image, and then run them to achieve accurate, reliable, and repeatable results. Machine vision systems also efficiently perform various types of inspections, verifying quality and assembly to determine whether items meet requirements and rejecting those that don't. For example, presence-absence checking for assembly verification essentially verifies the part components are present and in the correct locations. Defect detection identifies defects and calculates defect characteristics, such as position and size. Machine vision systems ensure quality by detecting defects, contamination, and functional flaws, such as irregularities. For example, detecting chip tablets in the pharmaceutical industry, or inspected the liquid crystal display by verifying the presence of icons, measuring backlight contrast, checking the characters are correct and that there are no missing pixels. Machine vision can also detect edge, surface, and other cosmetic flaws, and do inspection for completeness to ensure error-free production. For example, verifying that the product and package match in the food or pharmaceutical industry, or verifying the presence or absence of tamper-evident safety seals or caps and rings on bottles. Dimensional gauging essentially calculates the distance between two or more points on an object. Many consider gauging a subset of inspection, except instead of a pass-fail output, the vision system provides actual measurements or dimensions. In a typical gauging application, a camera mounted above or to the side of a part captures an image of the part to be measured as it enters the field of view. The image is then analyzed using gauging software tools which calculate distances between various points in the image. If you want a pass-fail output based on these calculations, you can configure the vision system to determine if the dimensions are within tolerance. In this type of configuration, if the dimensions fall outside of spec, the vision system sends a fail signal to a controller, which triggers a reject mechanism to eject the product from the line. Because vision systems measure part features within 1,000th of an inch, they are suitable for a number of applications traditionally handled by contact gauging. Machine vision systems also perform industrial identification and part recognition. They do this either by reading barcodes or characters printed on labels that have been attached to products, or by reading data matrix codes or alphanumeric characters that are marked directly on the product or package. Reading alphanumeric characters is called optical character recognition, or OCR. There is also optical character verification, or OCV. OCR determines the character identities without prior knowledge, and OCV confirms the presence of a given character sequence or string of characters. Machine vision can also examine patterns to identify items based on color, shape, size, or assembly. Direct part mark, DPM applications, have the code or character string marked directly on the part. It's commonly used in the automotive, semiconductor, and electronics industries for implementing error-proofing methods, enabling efficient containment strategies, monitoring process control and quality control metrics, and quantifying problematic areas in a plant such as bottlenecks. Traceability also provides improved asset tracking, enables part authenticity, service, and solutions, and provides unit-level data to drive superior warranty, repair, service, and support solutions by documenting the genealogy of the parts and the sub-assemblies that make up a finished product. Now let's talk a little bit about the different types of machine vision systems. Many people don't realize it, but there is such a thing as 1D machine vision. 1D vision systems analyze the digital signal, one line at a time, instead of looking at a whole picture. These systems generally look for the variance between the last 10 and earliest 10 acquired lines, One of the most common applications for 1D machine vision is to detect and classify defects on materials that are manufactured in a continuous process, such as paper, metals, plastics, and non-wovens. We also have 2D vision, which comes in different resolutions. There's a standard 640 by 480 resolution, 1024 by 768 resolution, and really high resolutions, like 1600 by 1200 and even higher. There's another type of 2D machine vision that we call line scan. What is line scan technology? Well, most cameras that people are familiar with, like the one in your smartphone, are area scan. Area scan simply means that the camera takes two-dimensional snapshots, if you will, and that's how it acquires the image. Just like we saw in the previous slide, you can have different resolutions in the images, in area. Now, line scan has a different way to capture images. Line scan builds the image line by line to make a full 2D image. A good analogy is to compare a photocopier to a fax machine or scanner. The photocopier is like an area scan camera. It needs to see the entire document to copy the picture. Because there's no motion, and since they need to see the full document, copiers tend to be quite large. Now compare this to a fax machine or even a document scanner, which sits on your desk. This represents your line scan camera. These devices scan the documents line by line to create an electronic copy. Line scan machine vision systems require motion, just like a fax machine or scanner requires that a document be fed in so that it moves as it scans to build the document into memory line by line. So when would you want to use line scan cameras? Line scan systems can generally do a better job than traditional area scan cameras in certain types of applications, such as inspecting round or cylindrical parts. If you try to look at the label of a bottle, you really have to rotate it or unwrap it in order to completely inspect that label. So that's a typical use for line scan. Second, if you need to fit vision into a tight space, for example, if you want to peek through rollers on a conveyor to view the bottom of a part, line scan systems can generally provide a much higher resolution than traditional cameras. So if you need more resolution, line scan can be a good choice. Also, because the line scan systems require parts to be in motion in order to build the image, they're very well suited for applications where products are in continuous motion. There are also 3D machine vision systems. These typically consist of multi-camera vision systems. 3D is commonly used in robotic guidance applications, where the vision system provides the robot with part orientation information. But there's another type of 3D vision system that's shown in the image on the right. And this is essentially a 3D laser displacement sensor that's inspecting the surface of brake pads for defects. Now, oddly enough, this device only has a single camera, yet it can produce 3D results by using a calibrated offset laser to measure things like the height of the surface, the planarity of a surface, or the volume of a glue bead. I want to take just a brief moment here to talk about line scan versus 1D and what's the difference. The difference between line scan and 1D is that line scan is still 2D vision, because once you build the image with line scan, you then just have a 2D image to analyze. Whereas with 1D imaging, we never really stitch the lines together to form a 2D image. We just look at the signal to determine the variance between the lines to detect and classify defects. Now that we're familiar with the basic applications and benefits of machine vision, as well as the types of machine vision, let's go over the key parts of a vision system. There are typically 5 components that make up a vision system. They include the lighting, lens, camera, vision software for processing, and communication. Generally, today's machine vision systems are divided into 4 platforms or types. There's PC-based machine vision systems, vision controllers for multi-camera applications, vision sensors, and smart camera vision systems, such as the yellow camera on this slide, which is actually a fully integrated machine vision system that includes lighting, autofocus optics, the camera sensor, processor, and communication. And choosing the right machine vision platform generally depends on the requirements of your application, with the key differences being the development environment, capability, architecture, and cost. So regardless of which machine vision platform you choose, it will usually include vision hardware, such as a camera that captures an image of the item to be inspected, lighting to enhance the contrast of the features that you are interested in looking at, and optics, which accurately represent the image to the camera by minimizing distortion and loss of resolution. This hardware works together with a processor to capture, digitize, and display images for analysis that it will use to generate answers, such as whether a part is defective. Finally, the resulting data is communicated to the outside world in a useful manner, typically using standard factory automation protocols. So to illustrate the sequence of events that occurs during the operation of a typical machine vision system, let's look at fill level inspection. When a bottle arrives at the inspection station, it is detected by a sensor which triggers the vision system to strobe a light and take a picture. And after the image is acquired and stored in memory, the vision software processes and or analyzes the image and outputs a pass-fail result. Faulty parts result in the vision system signaling a diverter to reject the part, and the operator can view rejected parts and ongoing statistics of the process on a display. But as we've learned, hardware and software make up the core of any vision system. By comparing specific features of interest within the image to store data that comprises a standard, vision software tools perform image processing and or analysis of the captured image. And there are a wide assortment of vision software tools and algorithms available for performing many different types of inspection operations that enable vision systems to make decisions about a part's quality, location, size, color, and identity. Because most of the machine vision hardware today, the components such as sensors, lighting modules, and processors used in machine vision systems, they're all mostly standard commercial off-the-shelf components. So it's very important to remember that the real differentiator between machine vision solutions are the algorithms. In fact, vision software tools and algorithms are the most critical element of a robust application. They should be considered the backbone of the machine vision system. And vision tool capability should be at the top of your list of things to evaluate when comparing various solutions to your specific machine vision tasks. Now, I want to briefly go over a few machine vision terms. Field of view is the viewable area of an object under inspection. In other words, this is the portion of the object that fills the camera's sensor. So if I've got a 3-inch part, then how big should my field of view be? It really depends. I can do a 4-inch field of view if my part is fairly well fixtured, and I'm just trying to count the teeth. But if my part is moving around a little bit, I might need more. And if it's moving around a lot, I might need even more. You know, at this point, it's good to ask yourself questions like, how is the part fixtured today? And how might we be able to fixture the part tomorrow? Sometimes fixturing could be as easy as installing a bar on the conveyor rail, so that as the parts go by and hit the bar, they're bumped over within a centimeter of each other. Other times, fixturing can be a bit more complicated. Working distance. So the working distance is the distance from the front of the lens to the object under inspection. Working distance is key, and it helps you figure out your resolution, which is the minimum feature size of the object under inspection. Because working distance and field of view are interrelated, you need to have those two things figured out when deciding which lens to choose. In this case, if you had a requirement for a 400 millimeter working distance and a 200 millimeter field of view, the graph puts us between the two lens sizes, 12 and 16 millimeters, right where you see that X there. We have two choices here. If working distance is fixed, we need to go up on the graph to the smaller lens size. We'd get a slightly larger field of view, about 240 millimeters, but at least we can see the entire part or feature that we're looking for. Of course, we could also go down to the larger lens, but we would do that only if we can get a bit further away to a working distance of about 450 millimeters. Depth of field is the maximum object depth that can be maintained entirely in focus. Depth of field is also the amount of object movement in and out of focus, allowable while maintaining a minimum desired amount of focus for your application. In general, you'll get more depth of field with a small aperture, or high F number, than with a wide aperture, or low F number. Depth of field decreases with increasing focal length, given equal subject distances. So in other words, if the subject distance stays the same, a long lens gives less depth than a short. A good way to kind of understand the principles at work here is to think of trying to thread a needle. I don't know about you, but this has gotten more challenging for me as I age. So now I usually have to squint. Now when you squint your eyes, you're essentially doing two things. First, you're creating an aperture and making it smaller, which increases the depth of field. You know, as you try to bring the hole in the needle into better focus, that helps. And the second thing squinting does is that it actually flattens your eyeball, which is like a little sack of jelly, which increases the focal length, or the distance between the lens and the focal point. So working distance can be long in some cases. For example, if you have some sort of robotic arm that's moving through an area and you want to protect your lens and camera from it, or maybe you need a big some extra working distance to make room for a special external lighting fixture between the camera and the object of interest. Or in other cases, you may have to be incredibly close. For example, if you're retrofitting the machine vision system into a space-constrained piece of existing equipment, working distance can have a very large impact on the actual level of performance you can get into the system, as well as affect the cost of the lens you need to use. A good rule of thumb is that you'd like your working distance to be 2 to 4 times the field of view you're trying to see. So if you have a 3-inch gear, for example, and you're using, say, a 4-inch field of view, the working distance should be between 8 and 16 inches. Sometimes this isn't possible, but if it is, it will give you the most amount of flexibility for performance and cost on the optics you're trying to use. Now I want to talk about 4 other ways to optimize vision system performance, and those are lighting, optics, filters, and image preprocessing. A lighting technique is a combination of a light source and how it is placed respective to the part in the camera. A particular technique can enhance your image such that it negates some features on your image, or by accentuating others, like silhouetting a part to allow measurement of edges while negating the surface details. And there are 5 basic techniques shown on this slide: a direct, back, diffuse on-axis, as well as diffuse off-axis, and finally structured. Lighting is one of the keys to success, so if you're interested in learning more about it, please be sure to download our expert guide on how to choose the right lighting for machine vision applications, which is available for download in today's WebEx presentation. All you have to do is click on the File drop-down menu at the top left of your screen, select Transfer, and you should be able to download the files. Alternatively, you can visit Cognex.com anytime and look under Resources at the White Papers and Articles section of the website. Next, we'll discuss the lens of the machine vision system, or otherwise known as the optics. As I mentioned earlier, the purpose of the lens is to capture the image and deliver it to the sensor. Generally, you'll find 2 different types of lenses on vision systems, either an interchangeable lens or a fixed lens. Interchangeable lenses are typically C mounts or CS mounts. The right combination of lens and extension tube will acquire the best possible image. A fixed lens is part of a fully integrated smart camera in general. Fixed lenses typically use autofocus. This could be a mechanically adjusting lens or even a liquid lens, and it will automatically focus on the part. Autofocus lenses usually have a fixed field of view at a given distance. Lens choice can dramatically affect the appearance of an image, so it would do you well to learn more about optics by downloading our expert guide on using optics to optimize your machine vision applications, or watching our recorded webinar on the subject. Optical filters all too often are only considered after the system is in place as a way to troubleshoot. Although they are a great tool to optimize an already existing system, they really should be considered in the conceptual stage of the application. Filters can be used to control quality and quantity of light, block all unwanted ambient lighting, pass only the output of lighting used for the inspection, and increase contrast and resolution. And if you want to learn how to gain better control of your machine vision applications with optical filters, I recommend watching our on-demand webinar on the subject, which you can also find on our website. Finally, I want to briefly mention image preprocessing. Image preprocessing filters alter raw images to emphasize desired features while minimizing undesirable features. And these tools allow your vision tools to work better and more quickly and significantly improve the accuracy and robustness of the overall system. The reason that you would want to use image preprocessing filters is that if the original image, although it might look good to our human eye, it doesn't quite come across correctly when it's being evaluated by the machine vision software. In the upper image on this slide, there are light spots right underneath the characters. You might think that having some light spots there is not critical, but in this case it actually is causing some problems and making it difficult to determine what the number looks like. So if you look down at the bottom image, you can see that we've done some image pre-processing so that the glare is no longer a factor, and now the numbers can be read much more clearly and efficiently by the software in the machine vision system. So you can learn more about this by watching our recorded webinar on the subject on our website. So to summarize, most high-volume products can be made better, faster, and less expensively using machine vision. The application categories of machine vision include gauging, inspection, guidance, and identification. The key components in a vision system are the light, lens, camera, or sensor, vision software for processing and communications. Learning more about optics, lighting, filters, and image preprocessing will help improve your vision system performance. And finally, if you're brand new to machine vision, we would strongly recommend that you don't go it alone. It's always best to get help from experts or work with qualified integrator that is familiar with your specific application. Thank you very much for attending. Do we have any questions, Karen?
Thanks, John, for that great presentation. Before we conclude today, let's move on to some of those questions that came in for you. John, the first one we'd like you to answer is, with so many types of vision systems on the market, how do I know which one is right for my application?
Well, specifying machine vision system platforms and components is highly application dependent. Many of our more experienced customers are experts and may know exactly what they need. But Cognex doesn't really require every customer to know which type of system is best for their application. That's why we offer a very broad range of products and have a team of direct sales engineers and a network of vision specialists that can help you select the system that best meets your requirements as well as your budget.
Okay, thank you. Next question. Why has data matrix been accepted as a standard in so many traceability applications?
Well, conventional barcodes have gained wide acceptance for checkout and inventory control in retail. However, traceability information requires much more data than can fit in a standard 1D barcode. To increase the data capacity, 2D barcodes, such as data matrix, have been developed. And data matrix allows the storage of more information, such as manufacturer, product ID, lot number, even a unique serial number on virtually any finished good.
Great. Thanks again. And the last question before we wrap up today is, in which production step do most manufacturers implement machine vision to identify labels printed with inaccurate information or applied on the wrong product?
Well, to identify labels printed with inaccurate or illegible information, the best place to inspect is prior to packaging or even during the converting process. That way you can correct the problem quickly and ensure that flawed labels or direct print packaging won't be applied to the product. In fact, the feedback gained by tracking individual label identity and validation of the accuracy of the information on the label can be used to control the converting process to improve yields and reduce scrap. So I'd say the best place to check if the label or package is applied to the wrong product is at the labeling or form-filled seal station.
Okay. Thanks again for your time, John. We hope you found today's webinar to be helpful and informative, and we look forward to seeing you at the next Cognex online presentation. Thanks for attending, and have a great day.